So you've probably heard that computers use just ones and zeros to represent numbers and perform computations called binary. And you've probably wondered, how exactly does this work? What physically is a 1 and a 0? Well, basically, ones and zeros are just abstractions of analog voltages that are present in the circuit. So a 1 just represents that a voltage is around 3.3 volts, usually. This is pretty standard. And a 0 usually represents that voltage is around 0 volts. Because we don't care the actual voltage in most situations with all this digital hardware. We care if the voltage is high enough to turn on a transistor or low enough to turn it off. That's all we care about. We just care if this transistor is on or off. A transistor is just a fancy word for a switch. And these switches perform the computations of the computer. So let's look at an example of what I'm talking about here. This is a NOT gate. And what it does is it takes in an input, let's say it's a 0, and it NOTs it. It outputs the opposite. So if it takes in a 0, it'll output a 1. Similarly, a 1 will become a 0. So what does this look like inside here? What is going on inside of this NOT gate? Well, an input's going to come in. It's going to go to 2 transistors, 2 switches. And these switches will perform the computation. Okay. So we have our input, we have our output. And then here, this device is powered by 3.3 volts. And this is just ground here. Ground just means 0 volts. That's all that means. Okay, well, we only care if we're going to get a 1 or a 0 at the output. So this is kind of the point of digital hardware and binary is, let's get rid of this 3.3 volts and just say it's a 1. We don't care what the actual voltage is. As long as it's close to 3.3 volts, we'll be fine. Same with this ground here. It's really just 0. It's a 0 volts, close enough, call it a 0. Okay, what happens if this input is a 1? That's going to go to both of these switches. Oh, I missed. This is supposed to have a little arrow here. And this switch here is active high, which means if there's a 1, it's going to turn on. So this switch will be on. Okay. This is an active low switch, which means if there's a 0, it'll turn on. If there's a 1, it'll turn off. So there's a 1, so it's going to turn off. So let's just erase it because it does nothing when it's off. And then I'm going to just erase this symbol for now to kind of show that this is acting as a wire because this switch is on. So 1 came in, went to both switches. This one turned off, this one turned on. So now a wire connects 0 to the output. So the output will be a 0 when we put in a 1. So that's this top condition here. What happens if we put in a 0? Well, you probably guessed that this bottom switch is going to turn off and this top one's going to turn on. So we can get rid of this. And this is going to turn on and just be a wire. So we put in a 0. Now this 1 is going to go through to the output. So we've now realized this condition here. And this output here can go to another gate. It could go to an AND gate. And that AND gate could also have another input coming from a different NOT gate. Whoops. Different NOT gate. And maybe that came from somewhere else. And then maybe this goes in to something and gets added. And then that result gets stored in memory. You can kind of see how all these gates will start to connect together to build all of this computational logic. And it really comes down to these transistors inside that perform these computations. And we only care if they're on or off for the sake of this. And that is where this binary stuff comes in. We don't want to know a thing about these analog voltages. We don't care. So I hope that was a good intro into what these ones and zeros actually physically represent in computers.